Today I will talk about the mechanism and kinetics of the oxidation of a propargyl radical by atomic oxygen. This is a joint work by my group at Florida International University and Carlo Cavallotti's group at Politecnica di Milano. The work was completed during my sabbatical leave in Milano last summer. Why do we need to explore the propargyl plus O reaction? Well, first of all, propargyl radical is a resonantly stabilized free radical, which is one of the most abundant intermediates in combustion flames because it forms in the pyrolysis of hydrocarbon fuels. Due to its high concentration in flames, it is considered the simplest and the most important resonantly stabilized free radical from the point of view of combustion chemistry. Because of its enhanced stability, propargyl reacts slowly with closed shell molecules and accumulates in flames. Self-recombination reaction of propargyl radical is the main source of the first aromatic ring in combustion, and propargyl also largely contributes to the further growth of PAHs. Of course, PAH formation competes with oxidation, in this case of propargyl, with propargyl radical oxidation reactions. The oxidation via molecular oxygen is slow, and therefore propargyl is mostly removed by oxidation by other species, such as oxygen atoms or OH, HO2, or CH3 or radical. What is known about propargyl plus O reaction experimentally? Slagel's group in 1991 measured the overall rate constant, and they found the reaction to be very fast, with the rate constant on the order of 10 to minus 10 cubic centimeters per molecule per second, practically independent of temperature and pressure. They also proposed propanol plus H as the main reaction products. Later, Choi's group used cross-molecular beam technique and theoretical calculations to explore the reaction products. In 2004, they detected OH using laser-induced fluorescence. However, their electronic structure calculations combined with Alarcon calculations of energy-dependent rate constants for unimolecular reaction steps found that H elimination channels should be predominant, whereas C3H2 plus OH are only minor products. In the second work, in 2006, they were able to identify the H elimination channels using H-atom Doppler profile analysis, and they also reported a more comprehensive account of the potential energy surface. However, the temperature and pressure-dependent rate constants and product branching ratios under realistic combustion conditions remain unknown, and this is reflected in unclear kinetics of the C3H3 plus O reaction in global combustion models. So our aim here is to obtain the rate constants for individual product channels and clarify the impact on the performance of literature kinetic models for kinetic simulations of various planes. First of all, we needed to determine the overall reaction rate constant, which depends on the entrance channel rate constants for the addition of oxygen to the radical site in the propargyl radical. Since the radical site is delocalized, we consider two additions, to the tail C1 and to the head C2 as in CH2 group. We used different kinds of multi-reference methods, CASPT2, with active space varying from 3 electrons on 3 orbitals to 11 electrons at 9 orbitals, and we used these VRC TST calculations either manually or using semi-automated VRC TST model in the automated ES2KTP package developed by Cavallotti's group. The calculations show that two first states are attractive both for tail and head addition. They are shown, potential energy curves are shown by red curves and blue curves on this plot, and one can see that the addition can occur not only on the ground electronic state but also in the excited electronic state. The plot on this slide shows the VRC-TST calculated rate constants, where the total rate constant is the sum of 4 different reaction channels. The combination of the C1 and C2 propargyl terminal sites on the ground and first excited states. The total rate constant is in quantitative agreement with the results of experiment. Comparing tail and head ignition, we found that branching ratios are nearly 50-50 with slight preference 0.52, 0.54 for the C2 addition. The excited state fluxes contribute between 35 and 41% to the total rate constant, and therefore the contribution of the excited state is very important. Also, when we compare the rate constant with the collisional rate, we found that at low temperatures the reaction occurs nearly with collisional efficiency. However, at higher temperatures the reactive flux is controlled by in a short-range transition state, and the reaction efficiency is a factor of 2-3 lower than collisional efficiency. The total reaction rate constant in hand, we move to exploration of overall potential energy surface, where we tried automated tools. First, they were used to find all possible isomers using metadynamics calculations with tight binding semi-empirical method and CREST package. And then different isomers identified by this automated exploration were connected by the search of transition states between them using the growing string method or GSM. Should be noted that our automated calculations allowed us to identify 12 out of the 13 isomers from earlier choice work and discovered 15 additional isomers. So totally we found, or this automated tool rather, found 27 C3H3 or isomers, and they were connected by transition states, and you can see the overall potential at each surface. But for the reaction kinetics, we focus only main reaction channels, which are shown in bold and clarify on the next slide. Here we improved calculations of calculated energetics using high-level calculations, targeting couple cluster method with single doubles and perturbative treatment of triples with the complete basis set. And we identified the main reaction channels. So here we can see addition of oxygen atom to the C2 atom, to the head, to the CH2 group, or addition to CH group or to the tail of propargyl radical. Additions to the CC bonds are also possible, but the cyclic isomers which are formed rapidly open ring and go to and process to isomers I1 and I2. Isomer I1, which is the product of tail addition, can dissociate to losing hydrogen atom to propanol and propadienone, or it can undergo hydrogen migration to form intermediate I3 and proceed to vinyl radical plus CO. Or another type of hydrogen shift can give isomer I4, and the latter can dissociate to acetylene plus HCO. I2 in turn can dissociate to P2 or to proceed to I4 and then to acetylene plus HCO. So you can see the most competitive reaction pathways are summarized here. Next, we used Alarcon master equation approach to calculate the rate constants of individual channels as functions of temperature and pressure, and to determine product branching ratios. The rate constants for individual channels are shown on this plot. And you can see that, first of all, we found that rate constants are practically independent on pressure. And this is due to the fact that all intermediates reside in deep potential wells, and decomposition transition states are at least 50 kilocalories per mole lower than initial reactants. And therefore, for example, at 1 atmosphere, no C3H3 species get thermalized by collisions, and only bimolecular products are formed. In terms of temperature dependence of individual rate constants, it is very weak, and the only exception is the vinyl plus CO channel, where we can see the significant decrease of rate constants with temperature by 67% from 300 Kelvin to 2500 Kelvin. In terms of branching ratios, the prevailing reaction products appear to be propanol plus H up to 60%, followed by propadienone plus H about 25%, and then C2H2 plus HCO and C2H3 plus CO. Also at 1500 Kelvin, the products of H loss contribute 85% of overall product, compared to only 15% for other products. And also, the contribution of the direct H abstraction channel appears to be insignificant. Next, we consider the impact of the newly calculated rate constants on the performance of combustion kinetic models that include validated pH formation chemistry. So we tested for this C3 v3.3 and crack models using open smoke. The updated kinetics resulted in microscopic changes of the model performances, especially at low pressures and rich conditions. However, negligible impact was observed for acetylene ethylene counterflow diffusion flames at 1 atmosphere. As seen from the parity plots in the bottom of the slide, the fraction of propargyl increases in C3 MEC due to slower reactivity of C3H3 plus O, but the peaks predicted in the updated crack model decrease for the opposite reason. The changes of C3H3 are reflected on the predicted concentrations of styrene, mostly produced by the recombination between propargyl and cyclopentadiene radicals. In both updated models, a macroscopic decrease in the concentration of vinyl radical is observed by as much as a factor of 2, and this leads to better agreement with the experimental data. The main impact of the new rate constants on the models is a better description of C2 species. In the original model, propargyl is consumed by oxygen recombination by about 15% to form propanol. And propanol then decomposes to acetylene plus CO, or by H abstraction by H atoms and addition of H radicals. In the updated model, the propargyl plus O pathway consumes about only 10% of propargyl, mostly producing propanol 7%, and then propanol can decompose via H addition to either acetylene or vinyl radicals, so that its concentration decreases in the updated model. This smaller production of H atoms via propargyl plus O and the additional consumption via H abstraction from C3H3 and H addition to propanol decreases the concentration of H atoms. And this fosters vinyl decomposition to acetylene plus H after the peak of vinyl concentration is reached. Neither of the two C3H2O radicals accumulates significantly at the conditions tested, as they are mostly consumed by unimolecular decomposition. In conclusions, we have explored the C3H3O potential energy surface using a variety of automated tools for discovering reaction paths via electronic structure calculations. Then we have selected the prevailing channels accessed by the propargyl plus O reaction for the Alarcon master equation computations of rate constants for individual product channels. For barrierless entrance channels, the rate constants were evaluated using VRCTST, and the theoretical value computed is in quantitative agreement with experiments as long as the contribution of C3H3 plus O recombination on the excited electronic state is included. We found that the prevailing products are propanol plus H followed by propadienone plus H with minor yields of acetylene plus HCO and vinyl plus CO. The calculated rate constants were utilized in kinetic simulations of premixed laminar flame of acetylene, ethylene, alene, propane, and benzene, and microscopic changes in updated model performances have been observed at low pressures and rich conditions. The smaller consumption of propargyl via C3H3 plus O, the negligible contribution of HCO plus C2H2, CO plus C2H3 in vinyl formation, and the smaller concentration of H atoms, shifting the net flux of the vinyl decomposition to acetylene plus H from backward to forward, make the model predictions of C2 species closer to experimental observations. In the end, we would like to acknowledge our sponsors, the Department of Energy for the work at Florida International University, and ICSC and NEST for the work carried out at Polyme. Thank you for your attention.